check that out. Today, we're going to talk about pointers and the fact that pointers are big and inconvenient sometimes. You know, we live in this world of 64-bit computers. You know, we still run 32-bit programs pretty often because our CPUs will do both the 32 and 64-bit, and our operating systems tend to do both. You know, 32-bit, especially if you're making a game, is really a problem now, right? You tend to need several gigabytes of data, and 32-bit won't let you address enough data, and so we tend to go for 64-bit. Now the problem with 64-bit is that pointers are big. And then when I'm designing a programming language that tries to give you more convenient facilities than just raw pointers like you have in C or C++, those other things are also big, right? So in this language, there's a built-in array type and a built-in string type, and both of those actually look the same. They're like a count, right, for some number of bytes, and then a pointer to data. And on a 32-bit operating system, these would only be 8 bytes each, or in a 32-bit program. In a 64-bit program, there's 16 bytes, which starts to feel pretty large for just like a string, right? But it has to be that big because, you know, what happens if you have a string that has an unsigned 32-bit length or something, then you can only load a 4-gigabyte string, and which seems big, but is not really big, given that, you know, most PCs have these days at least 4 times that much in RAM, right? So you should, if you wanted to load a 20-gigabyte file, you should just be able to like load it all into one string. And if you can't do that, then you have to start tiptoeing around what your program can and can't do, right? So for the sake of generality, if a program is going to provide some facility that standard libraries are going to use and that user programs are going to use, it has to be able to handle those situations robustly, which is why like the standard string, you know, lets you do 64 bits worth of stuff, and so does the array, right? However, game programmers like to optimize things, right? You know, if you have a struct and it's got like 5 strings in it and like 2 arrays and whatever, which is not at all uncommon, then the sizes of these things start to get really big really fast. And we'd like to crunch those down. And if the language doesn't give people a way to crunch these things down, they're going to make their own facilities for representing strings and arrays in smaller packages. And then the problem is they start to lose the convenience of having a standard way of talking about these things. If you start having to manually convert to the standard thing and back, then why do we have these native types at all, right? So one way to make things smaller is to use relative pointers instead of absolute pointers. And by relative, today we're going to talk about pointers that, rather than storing some 64-bit number like a void pointer would typically be, that could point to any virtual address that could be represented, today's pointers point relative to their own location, right? It's like instruction pointer relative addressing that's already built into the CPU, right? And this is the programming language version of that. So I'm just going to dive into some demos. If you don't understand why you would want this or what it does, hopefully this will become clear as we talk about this stuff. So first, I'm going to do something that uses regular pointers and is totally conventional and shouldn't have any surprises. And the reason I'm just doing this is to lay down the establish what we're doing, and then we'll change it up as we go from example to example. So here's a procedure called nodes absolute. I'm defining a struct called node. It's got some value that's a data. It's a signed 32-bit number, and it's got a next pointer to another node, right? So this is just like you would build a linked list out of these if you wanted a linked list of numbers, right? Now I'm going to allocate 3 nodes, A, B, and C. And instead of allocating them off the heap generally, I'm going to do a different thing today, and I'll show you what that is. I've got this thing called buffer up here, which is just an array of 1,000 unsigned 8-bit numbers, right? 1,000 characters. And this is just going to be a flat memory space that we're allocating things out of. We could very easily build, you know, a more sophisticated allocator that dynamically expands the space and all that. This doesn't do that, and it's just for the sake of simplicity today that we're doing this. So we had better not allocate anything bigger than 1,000 bytes, but we're not going to today. Anyway, so I've got this thing cursor that just starts as the whole buffer and then eats its way into that, and that's how we're controlling what we allocate. So we're just allocating things from beginning to end in this buffer linearly, right? So I'm calling allocate, and we'll look at that. Oh, it's right here. So we just, we're passing a type as a second argument, right? So we take the size of the type, we bump the cursor, here cursor gets passed as data. So we bump data forward by the size, and then we return the pointer from before we bumped it. That's all that this does. So we're allocating 3 nodes that way, bumping that cursor forward every time. We're setting 3 different numerical values, 15, 4607, and 69,105. And then I'm going to set this next pointer to make a little linked list out of this. So A's next pointer is going to be B, and B's next pointer is going to be C. And then I'm going to print out the size of the node, and then I'm going to call this print nodes procedure, which just starts at the starting node, and for every node, it's going to print, it's keeping track of some index of what node we're on, 0, 1, 2, 3, etc. It's going to print the index, and then the value field of this node, right? And then increment the index and go to the next pointer. And when node is null, it breaks out and says done, okay? This is totally beginner linked list situation. Nothing too special. Let's run it. And we're just going to run from the compiler today for expedience. So we're not even building a separate executable. So we're running this whole program from the compiler. And here we go. So test number 1, node size is 16, right? It's 16 because a pointer, as we said, is 8 bytes. 64 bits is 8 bytes. And then this, it's 32 bits, which should be only 4 bytes, but then this needs to be aligned, right? So just like in C++ or C or most other languages, there's some padding between these 2 elements, right? So this ends up actually taking 8 bytes, 4 of which are wasted, right? And so, so our node size is 16 bytes. And then we're navigating that linked list. Node 0 has 15, node 1 has 4607, node 2 has 69105, and then we're done. So this works. That's all we're doing is demonstrating that we can build a linked list. Certainly not much exciting about that if you've programmed in just about any language, right? So we're going to do the same thing now with relative pointers. And it starts with exactly the same code with one difference. Let me show this side by side. Try to line this up in Emacs. So at the top of the screen, I'm going to put nodes absolute, and on the top of the screen on the right, I'm going to put nodes relative. So you see it's all the same. I go on and elaborate a little bit more down at the bottom, but sort of from here to the top, it's all the same on both sides, with one little difference, which is here. Here I'm saying next is not a absolute pointer to a node. It's a pointer that's a relative signed 32-bit number. So the little tilde means relative pointer in a type context, right? And this is the type of the pointer, signed 32-bit, right? Now what's going to happen then is this is stored internally as a 32-bit number. This is a 32-bit number. And then together, that's only 64 bits. So this node is 8 bytes, which is half the size of this node, right? And yet it's got a pointer in it. How is that pointer different from a regular pointer? Well, it can't point to anywhere in memory. It can only point to about 2 gigabytes plus or minus its current position. But if you're controlling your memory allocation, right, and you sort of know where things can end up and what is the range of space that things could possibly point to, then this is a very nice way to save some space. So we're doing the same thing. We're allocating 3 nodes. We're putting values in them. We're setting up the links. Here, I'm going to C's next pointer would have been null already because this field is initialized to null, especially here. Notice we didn't set it here. But here I am going to set it, and it's just to explicitly point out that even though these are relative numbers, they also have a provision for encoding null, right? If you're at some, you could be at some address higher than 4 gigabytes away from 0, which is the representation for null, and technically be unable to point at 0, but we have a value reserved in the space of the relative pointers to say, oh, this pointer is null. And that value actually is 0. So if you memset your struct to 0, then all your pointers point to null, whether they're relative or absolute. Okay. Anyway, so we do the same thing. We print out the node size, and then we print the nodes. So let's go here. So now test number 2, node size is 8, and the nodes have the same values, and we're done. So that's cool. So now we're going to look a little more into how the relative pointers work. We're going to make another node D. It's going to be allocated the same way as A, B, and C. And then we're going to copy A into D. And when you copy, so like I said, this pointer is just a signed 32-bit number. But you want that number to automatically change. You want it to act like a real pointer. Let me put it this way. If you start with code that's like this on the left with an absolute pointer, and then you put in a relative pointer instead, then the behavior of the code, this is arguable, but we're starting with the premise that the behavior of the code shouldn't change, as long as your program is still correct, right? As long as you can point, as long as the place that you want to point is within the valid range of this pointer, right? And so if you start out with A and its next pointer points at something, and then you assign that into D, D has a different address than A. And therefore, to point at the same destination, D's pointer has to change in value from A's pointer. And so the assignment operator does this automatically, right? And so here we're just going to say D minus A is whatever the difference is in the memory locations of D and A. And then we're going to print out these two nodes, and it's going to show us the contents of the pointers. So D is 24 bytes later than A, which totally makes sense, right? Because it's 8 bytes per node, and A plus B plus C is 8 plus 8 plus 8, which is 24. A is a node. The value, which is this sign slot, is 15. This is no surprise. That's what we set as the first thing. And then next is this relative pointer. That's what the R means. And it says 4, meaning pointing 4 bytes later in memory from the position of the pointer, which again is no surprise because A is pointing to B. B was allocated immediately after A. And the size of this pointer, well, in this case, the size of this pointer is 4 bytes. We're pointing 4 bytes later. And then this is printing the absolute address, actually, in hex. There's no letters in there, but that's a hex number. So the print statement is decoding this relative pointer for us so we can see what address it points to. Now remember, I said, then I copied A into D. And this notation is the same. This is just what C++ version of that would be, just star D equals star A, right? I'm putting the contents of A into the contents of D, right? And equals adjusts the relative pointer for us. So the value is the same. That's no surprise. The relative pointer now points 20 earlier in memory, right? It's minus 20 because B was allocated way before D. But the absolute address is the same, right? So when you dereference this pointer, you automatically get this address. And we point to the right thing. And we prove that by then we say print node starting at D, right? So now we're following the linked list from D to B to C, right? And so here's D, B, and C, and then we're done. So that's all great. Now the other thing to note is we didn't have to do any weird macros to decode this pointer. And it's totally type safe, right? So the compiler decodes this to a pointer to a node, right? It's exactly the same type as this once you've pulled it out of memory into a full-size pointer. So the goal of the language support is to make it transparent to be able to use these and to have all the same kinds of safety that you usually have. Because when programmers sit down, we're going to go through more examples later, when programmers sit down and do these kinds of things that we're going to show, often they'll hack them together with like just integer offsets in files and stuff. And that kind of gets messy and it's easy to make mistakes. And what we're doing is we're giving it the solidity that strong compile time type checking usually gives you. Okay. Now, we allocated all this stuff into linear memory. right? So I'm just going to save that linear memory to a file because we can. Normally you don't think of as a linked list as something that you can save to a file, at least without doing some complicated serialization process. But here it's all just in linear memory. As long as I'm going to load that file back on a machine with the same architecture, so the numbers are the same size and the same endianness, or as long as I know how to translate it, then this is a valid way to save the information. So I'm just going to take a new string that points at our buffer. Remember, buffer was this thing at the beginning. I'm just going to point at that, and I'm going to say, well, it's as long as however far the cursor is. And then I'm going to write that to a file and assert that that succeeded. So that's just an example that you could do that. Now there are some limitations that you take on as soon as you do this, right? So for example, as I've said, a relative pointer can only point so far in memory, right? So if you try to copy something onto the stack, notice that D over here, when I made D, it went into that same memory buffer as everything else, right? If I try to make something on the stack, like this thing E, and I say, well, E gets the contents of A, then I'm probably going to overflow my pointer and point it somewhere nonsensical, because you have no guarantee that your stack is anywhere near this thing. In fact, it is when we run in bytecode, but it's not when we run in compiled code. So this is not something that you want to do. You would get a runtime error when we detect overflow, but I don't detect overflow yet. We'll talk about that in the Q&A or maybe next time. We will detect overflow because it's important. But today we're just demoing the functionality. All right, so just as a sort of a compiler test, I implemented a super node that contains nodes just to make sure that if you have nested structs that the values get translated. But then that raised a question of like, what exactly would you like the behavior of relative pointers to be in this case, right? So I've got this thing. I'm setting the values of A, B, and C, and I'm setting A's next to C and C's next to B. So it's very analogous to what we did earlier. However, these things point internally to themselves. And it raises the question of what we want to happen. So if we make a second supernode and copy the first one, what should happen? If we follow the thesis that I said earlier about the behavior should be exactly the same as it is with pointers, then M should then be pointing into N's nodes after this copy happens. And that's what I've done for now. We'll show this in a second, but I've preserved the semantics of absolute pointers in this case. However, it might be that maybe one reason we want relative pointers is because they can be better than absolute pointers. And then we actually want equals to detect when pointers are pointing within the copied region and not alter them so that they end up pointing to a place in the new copy. That is a possibility. However, if you want those semantics right now, you can get them anyway. So you could say, mem copy, you could do that, right? Because mem copy will copy the bytes without altering them. And right now equals does alter them. Anyway, so here's what happens. So here's the addresses of these two things. N is this supernode. It's got a note, hello sailor, and it's got some nodes that point at each other, right? Just like before, except this time B is last and has a value null. Should I make this wider? Yeah. Anyway, so then we made M, which is a copy, and you'll notice that the places that M points are the same absolute pointer values, right? Because I preserved the behavior of absolute pointers in this case. Not completely sure that's the right thing to do. It's interesting. All right, so let's go back to main and see what is next. Read from file. So remember, back here, I wrote this data out to a file, and just that was all that we said about that. Well, we can come back and read that data again, and I just want to show how easy it is to use this data when it's been written out in this way, which is, again is part of the power and utility of having relative pointers like this, right? So before, our declaration of node was in a local procedure, so it's not in our scope, so I'm just putting it here again. But it's the same declaration where our next pointer is a pointer to a node, but it's a signed 32-bit pointer, right? So I'm going to load the file into a string. That's what read the entire file does. It just gets the size of the file, allocates a string that big, and like f reads the file in, right? We print out how big the file is, and then to print the contents, I'm going to cast the file data to a pointer to one of these nodes, and then I'm going to call print nodes again, right? So we're loading structured data full of pointers from a file and doing no processing, right? We're not like looking up pointers and stuff, right? So here we go. File data is 32 bytes, contents 15, 46, 07, 69, 105, done, right? So, you know, this is in a game engine or any other modern multimedia application that is asset heavy, where you want to load assets that have pointers and arrays and strings and other stuff in them, like, for example, you know, 3D meshes or entities or something like that. Then the kind of loading that you want to do is this kind of loading, where you just pull in the data, or maybe the data is already there because it's part of a bigger package and you're just pointing at a place in the data, and you don't want to have to do processing to it. You don't want to have to like unpack things into arrays and allocate a bunch of stuff on the heap and load other chunks from other files, right? And you don't want them in like a JSON or XML or other such relatively lame file format, because that stuff is slow and it treats your memory badly, right? What you want to do, what all good game engines do, is they load memory in a chunk and point at it, right? And so what this relative pointer support does is it lets you do that without losing first class programming language support for what you're doing, right? You don't have to do a bunch of hacky macros and weird things. All right, what's next? Someone is saying it's an offset relative to this. It is not an offset relative to the this pointer. There's no such thing in this language. It's an offset relative to the pointer itself and not the start of the struct. I won't go through an example illustrating that because it's not that important, but the pointer doesn't know where the start of the struct is, and there may be no such thing. Okay, let's talk about arrays. Wait, was that the right? Yeah. Okay, so I mentioned before that arrays, full-sized arrays in the language look like this. They're just a packaging of a length and a data pointer, and you might say, well, why do you do that? Well, it's good for a lot of reasons. You know, in C or C++, well, in C, if C++ people tend to get the modern C++ disease and do all sorts of crazy things, but in C and in C++ game style, you end up passing two arguments around all the time when you want to talk about an array, and the debugger doesn't know these things are associated, and etc. When these things are put together, the compiler can range check them and do all sorts of good stuff for you, right? So, you know, it's very convenient to have these packaged together, but like I said, if they're too big all the time, people may not want to use them. So here's an example of using arrays with the same relative facility, and instead of instantiating stuff by allocating in the data segment, I'm just going to do it on the stack this time. So I'm going to have 3 integers in an array, fixed size array here. I'm putting the numbers 3, 4, 5 in there, right? Simple. And then I've got a, you know, an array of unknown size. I don't know what to call this. Like, I think Go calls this a slice. It's just this count and data pointing at this, right? So the count gets 3, and the data gets the pointer to the base of this array. I don't like the word slice because it sounds very active. It sounds like you're acting on the data to cut it up, but that's not what's happening. You're just taking a view of that data. Anyway, so we're just going to iterate over there and print y, whatever, and then each number, right? And so here we get y3, y4, y5. Now we're going to do the same thing with x, but x is an array with 32-bit pointer, right? And we're going to assign that to source as well, and we're going to for x and print, and look, that works. And then I'm going to say z is an array of int again, and I'm going to assign that to x instead of source. And that's just demonstrating that, look, I can implicitly convert from this array to one of these and back out to a big array anytime I want, right? I didn't have to cast or do any weird macros or anything here, right? So for z, print blah. and z works, right? And so size of y, which was the big array, is 16, and size of x is 8. Now it's 8 because in addition to making the pointer small, we also make the count small, which is not a priori necessary. You can imagine some kind of syntax where you use this tilde to specify two sizes or something, but right now it doesn't really seem to be worth the complexity of doing that. So right now I just have the size, the count and the data are always numbers of the same size. And we'll see if we have real world use cases that need more versatility than that. We'll look at that later. There is more versatility that we will probably add to arrays, but it'll probably be about not having a count, like saying this array is the same length as this other array or something. Yeah. So now we're going to switch to a different example, and I'm going to do it again. I'm going to go really quickly through doing this thing with absolute arrays again, and then we're going to go relative. So this is going to be a thing called a holder. It's just, you know, a key value store where I've got some array of names and an array of values that's parallel. So we've got the same number of items in both, and the names correspond to the values, right? And I'm just going to, with absolute arrays, I'm just going to do messy heap stuff. So I'm going to say it's a new array of string, new array of float. I'm going to set names, right, to these three strings. I'm going to set the values to some relatively arbitrary numbers. I'm going to make a new, so new is just like C++ where it calls, you know, our equivalent of malloc. It's not as messed up as C++ is new. And I don't know if this is, well, let's not go on that tangent. Anyway, so I'm setting the names and the values, and I'm calling print holder. And print holder just does this, where we say what the size of the struct is and say its name, right? This is polymorphic, note, so that'll be important. Then for everything in the names array, we get the value at the same index as whatever that name is, and we print out the name, a new line, and then some spaces in the value, right? So when we print this first holder, we get size of holder is 32, right? Because there's two arrays, and each array is 16 bytes. And it says Cosimo, Viola, Ottimo, Massimo. That 16 bytes, by the way, is not the contents of the array. It's the data and count that points at the contents of the array. So it's a little bit, it's the size of the storage of the array view or array slice or whatever you want to call it. Okay, so that's just the regular old absolute part. So the relative version is much like what we did with pointers, right? So I've got this names array. It's an array with signed 32-bit elements, and values is an array with signed 32-bit, not elements of the array, but data and count on the array, right? And then we're doing all the same stuff. And let's not, this is literally the same code. So we'll just look at that and show that that works, except that the size of this, this is called holder 32 now, and the size of holder 32 is 16 bytes. Boom, same stuff. Now, again, just like those arrays, the packed, oh, I got ahead of myself and talked about relative, oh, this is wrong. I'm not using relative strings yet. Relative strings is going to be the next topic. So let's skip this. Anyway, that's just showing that just like relative pointers, we have relative arrays that work the same way. Now, we can take that a step further. So instead of deciding a priori what our packing is going to be, maybe we want to be more versatile than that, right? So I'm going to make this thing called holder sized, which is some struct. It's got arrays of names and values, but it's got a parameter, which is like some type that I'm going to pass it. And the arrays, and actually this string here too, we'll talk about size strings in a minute, as I said, but you know, the arrays are all going to be sized and relative based on this pointer, right? So I'm going to make a holder sized of 16, and I'm just going to print the size, and I'm going to make a holder sized of 8, called another holder, and print that size. And they should get smaller, right? So size of holder is 8, size of another holder is 4. So we're just instantiating these structs at these two different sizes. All right. Now we're talking about relative strings, as promised. So just like arrays, a string is a bundling of two things, a count and a data. And again, it's because, zero terminating your strings, as is the C convention, is not necessarily a very good idea for a lot of reasons. It's very convenient to know how long your string is much of the time for both security and speed purposes. However, that takes space, and we already said pointers are big, and then when you double the size of a pointer, that gets kind of big, and sometimes you don't want them to be that big. So again, we're just applying the same technique. Here we're doing it on the stack, so we're copying a string into this buffer on the stack. B is some string with 16-bit count and data this time. And I'm setting the data to where this buffer is and the count, right? And that's it. So then I'm just saying, okay, here's the size of a full-size string and then a size of the tiny string, right? So size of A, full-size string, is 16 bytes. Size of the tiny string is 4 bytes. And then I'm printing B just to prove that it works. And B is hello. All right. Now the reason I had to do this little bit of funny thing with copying this into a buffer on the stack is because B is on the stack right now, and he can't point that far, right? Especially because he's only 16 bits per member. However, you wouldn't use a 16-bit pointer string on the stack in reality. You'd use it in a struct somewhere. So, doing it on a stack is a little bit funny. I don't know why I did it that way, I just did. I got tired of defining structs. Okay, so now we're coming to the fun part. So I started out showing this holder thing. Actually, no, I didn't start that way. I started with the linked list node, but with any data structure like this that has pointers to arbitrary data, like I said, when you want to do the game engine thing, you want to load it fast. You want to have it packed into memory, and you want to load it. However, you also sometimes want to operate on it. So like, if I want to render a 3D mesh in a game engine, then during runtime, when the player is playing the game, I probably just want to load the mesh really fast and not look at the memory at all, except for, I don't want to process it. I just want to load it and use it, right? But there might be other parts of my code that want to process that mesh, like maybe, recompute the vertex normals based on something, or add a second set of UVs to it, or there's all sorts of things you might want to do. And you don't tend to do those things during gameplay time if you don't have to, right? And so you end up wanting to manipulate two versions of the mesh, one that's not packed together and one that is. And so I've showed all this stuff so far of you can pack this thing and save it to a file, and isn't that neat? But, you might be thinking, oh, isn't it just annoying work to have to pack something that way? Isn't that tweaky? Yeah, it's great that the language is providing type checking and stuff, but I still have to do all this tweaky packing. And actually, you don't have to. So I wrote a little demo of automated packing of something into a linear buffer with relative pointers. So we're going to start by calling holder with absolute arrays, right? So this is just exactly the same thing that we did at the start. It's just calling this procedure that constructs this holder on the heap and prints it out. So here we are again. This is just the same thing, nothing new here. Now, I'm just going to tell you what this does, and then we're going to go back and look through this procedure pack. But this procedure pack takes the elements of this struct and packs them into a holder struct that is sized by the second size, and that's all contiguous in memory and relative pointers, right? So at the end of this, we're going to have these arrays, and then all the contents of all the arrays flattened contiguously in memory that we could save out to a file or do whatever we want. And the first thing we're going to do is just say how much memory it is and print out the memory, right? And then we'll print out the data to prove that it's actually data structure. So we're treating it both as a linear data structure we're treating it both as linear memory and as structured data. And that's a very powerful, to have both of those views on data at the same time is very powerful. And the first thing I'm going to do is convert it to 64-bit relative pointers. Why am I doing that? Well, they're not any smaller, but it does give you that serializability that you get with the smaller relative pointers, and they could point anywhere in memory, which is very convenient. And just as a diagnostic, this will tell us how much memory our data structure is using, which is a useful thing to know. Not counting, heap fragmentation and all sorts of other waste like that. Anyway, so we're making a result 64 that's packing this thing with S64 pointers. And here it is. It's 117 bytes. Here's all the bytes. You'll note that a lot of those bytes are 0 because relative pointers, when they're 64 bits, if they're pointing to anything nearby, which most of these are, compress really well because they're mostly zeros. So, this thing, these are all the pointers, right? And then eventually we get to the string data, and these are mostly ASCII characters representing those names. And then there's some floating point numbers in there as well, right? So that's 117 bytes, which is what this original thing was using. So that's good to know. Most people have no idea how much their data is, right? So then we're just going to do the same thing. I'm going to say, okay, now let me pack that thing with 32-bit pointers, relative pointers again, right? And let's print that out. So we do that with 32-bit pointers down here, and it's 77 bytes. Look, it's fewer numbers because we're packing fewer zeros. All the numbers at the end are the same, right? It's just we have way fewer zeros here. And then we'll do it again. It's like, hey, let's do it as 16-bit pointers. Oh, that's 57 bytes long, right? And then let's do it with 8-bit pointers. That's crazy. But this is a small enough data structure that everything is within 127 bytes forward and back. In fact, it's within 47 bytes forward and back because that's how big it is, right? So that's a substantial size change. We got something from 117 bytes down to 47 bytes just by ensmalling the pointers. And after each one of these, we're calling print holder. Remember, print holder was polymorphic, right? Print holder takes anything of type T, and then, this is like a C++ template where as long as we can do the things that we try to do down here with it, it'll work. So we're actually passing 4 different data types, right? A holder size of 64, a holder size of 32, and so on. And we're printing this, and it works all 4 times, which is just proving that this packing down of the data that we are doing is correct and maintains all the original data, right? Now, like I said, though, they're not just one-way serialized buffers. They're also structured data, and we can treat them in both ways, and that is very powerful, right? So here's what we're going to do. We're going to take this result 8, which is the smallest one, and we're going to do some structured data. Well, first we're going to copy it. We're going to copy result 8 to a new string called copy, and then we're going to cast that data to a holder-sized S8, right? So we've got a new S8 holder-sized. And then I'm going to do some stuff. I'm going to swap the first 2 names. So I'm indexing this names array, 0 and 1, and let's swap those. And then let's iterate over all the names, and we're going to turn them all to uppercase. And then this is a little wrinkle. This full-size string here is not important to talk about right now because it'll be fixed, I think, in the final language. But there's a slight wrinkle where I have to insert a helper function here. So it's not completely transparent that I'm using relative pointer strings, but it will be. If someone wants to remind me to talk about this in Q&A so we don't sidetrack now, we can do that. But anyway, so we're going to uppercase all those names in place. And then we're going to set the values to new floating point numbers and do some math on them. And then we're going to print the holder, right? This new one that we just modified, right? So H points to copy. So we're going to print that. And look, they're all uppercase. And they've got the different numbers. So that's great. But let's prove that that was an independent copy and the original was untouched. So we print holder of the independent result 8, which still is sticking around. And that's here. The original copy of holder 8 is untouched. So we just essentially, with a mem copy, so I called copy string here. Let me show you what copy string does. Where is it? So copy string, when we copied result 8 into copy, that's just this. We say, okay, we make a string, right? Set the count to be equal, allocate the data on the heap, and then copy, right? So this is just a mem copy is all that's happening. So we're mem copying this thing, but we're getting a data structure back that we can treat as a data structure. That's great. And then as the last thing for this procedure, we're going to do something really fun. We're going to take copy, which is this version that we just futzed with and made all uppercase and stuff, and we're going to print out the bytes, kind of like we were doing here. We're going to print it out more like code, where there's a declaration and some commas between all the bytes. So it's going to look like this. And this code right here is just building that string, and we print it out. And that's exactly what we're looking at here, right? The code string to add is this. So now we're going to compile this into a totally separate program. We're going to make a new workspace in the compiler. We're going to set the build options to make an executable called separate program. Because remember, this whole thing was running in the compiler the whole time. We're going to add a file called demo relative pointer separate program. Whoops. Let me go to it. And then we're going to add this data payload string that we just printed out as well. And this separate program, all it is it's going to have some of the same stuff we had. We had this holder sized, right, which we can instantiate at any size. We've got print holder, which is exactly the same. And then we've got main. This is the whole program apart from importing the print function, right? So we've got none of the other stuff we were doing. None of this constructing the value or anything. We're just including the value in the global data, right? So we print welcome to the totally separate program. We point holder at this data payload, which is just bytes, right? And then we print it by iterating over the names and values and doing all this structured data stuff. And so I can run that. I can run tests, demo, relative, pointers, separate, program.exe. Did I get that right? Demo, relative. Oh, wait, it's just called separate program. I gave it a shorter name. I was all confused there for a second. Did I typo that? No. So it says, welcome to the totally separate program, and it prints out that data that we futzed with and messed with, right? So it's data we just exported to a separate program, data containing pointers, right? And so that's what's nice about relative pointers. And we didn't have to do anything crazy, right? We just had to say, these pointers are relative. So that's great. Okay, last thing. So I think this is the last thing, yeah. So the last thing is just to make a point that instead of instantiating things always with a signed number, like S16 or S64 to make something a relative pointer, if you put void there, that'll make it an absolute pointer just like it always was. Why would you want to go through all this and then put void? Well, maybe, for example, in the game engine case, like I was talking about, you want to make a triangle mesh that the one that you operate on has absolute pointers because you're just going to be messy with the heap and whatever, right? And then when it's time to pack it down for gameplay, you instantiate a version of that with relative pointers, whether they're 64-bit or smaller, you know, who really cares, that you can then just serialize with memcopy or saving to disk or whatever, right? So here's just an example of that. I have this node general that can have any type of pointer. This is the same as the linked list node at the start of this talk. And here I'm just going to set the next pointer to itself just to do that. So I've got a node 16, node 64, and node full, right? So node 64 is the same size as node full, but these are relative pointers and these are absolute pointers. And I'm just printing these, right? So going back to the original program. So here A, right, has a pointer pointing to itself. B has a pointer pointing to itself. C has a pointer pointing to an absolute address, not a relative address. Now, the next project, which I didn't do for today, but I hope to demo this in the future, is that I'm actually going to use this on a large data structure, like the triangle mesh in the game engine, because everything that we've done should map to that straightforwardly. There were a few other things I wanted to do on my compiler to-do list before I did that, so I haven't done it yet. Now, I mentioned that we should look at what this pack function is. So remember, remember when we made these holders of different size? I said pack makes a holder of a particular type. And so I'm just going to show you. Well, it makes actually not a holder of a particular type. It makes any packed version of any particular type. And here's what it does. So I'm going to leave this usage code on the left so you can remind yourself how it was used. So on the right, okay, it takes a pointer to some type, right? And then the pack type, $, is our very verbose way of saying we need to know what this is at compile time. We demoed that in a previous talk a long time ago. So the pack type, I'm probably going to change it to actually a single $sign so it looks like that eventually. But anyway, so we tell us what the type of the pointers should be, right? And what we do is we just get the type info, which tells us what all the members of the struct are, and we iterate over that. I'm just going to go through this really loosely because it's not that. This isn't a fully robust implementation yet. It's a demo implementation that doesn't handle all cases. But basically, we look at all the members of the struct, and if there's an array member, then we know that's got pointers in it. So let's note later that we need to write out the pointers. We need to write out the contents of this array and then backpatch the pointer to point to the contents, right? This is totally, if you ever serialize stuff, this is totally typical, right? So we say, oh, we've got a thing to pack. Here's where it is. Here's the source address of, where the pointer is pointing to, right? Or here's the address of the source pointer, right? And here's the destination address in the bit stream that we're serializing, right? And we just make a note of that. And then we put down zeros for now. So we just say for now, oh, the count on this array is 0 and the pointer is 0. But we're actually going to overwrite those later on, right? And if it wasn't an array, we just copy the member. And the reason why this isn't a full implementation is because it's not handling like string here or one or two other things that would be important to handle. Pointers to other structures, stuff like that. Anyway, so once we've gone through all the members and we've noted all our things to pack, now we've finished serializing the body of the main struct. We couldn't serialize that other stuff yet. You might think like, oh, well, let's recursively serialize in here, but then you break the memory of the body of the main struct, which you don't want to do. So you finish writing out the main struct, and then for everything that you said, oh, this is a pointer that we need to follow up, then you go and serialize all those contents. So I said, well, maybe it's an array of strings, in which case, we do this. Oh, actually, sorry, that's not array of strings. Maybe it's a string member. I don't actually add string members. So this is, like I said, it's an incomplete implementation, right? Or if it was an array, hey, maybe it's an array of strings, in which case, we do a special thing, otherwise blah. So all it's doing is linearly serializing and in not a particularly special way. But as I said, what that does is it automatically takes some type that whatever it is just all over the heap in memory that could be pointing to anywhere and could be very slow, and packs it into a version with relative pointers of a potentially smaller size that we can then load directly off disk. And that is everything that I wanted to say today. So I'm going to take a very short break and get a drink, and we can do questions and answers.